All right, hello and welcome to GlobeBusters, Season 14, Episode 18. Today, Shane's going to be bringing us through the intricacies of gravimetry. uh, now,
Nice.
now there is an
He did
official
it.
interpretation of how to pronounce that, but you guys are free to call it gravimetrometris or whatever you guys want. Really, anything is fine. So Shane's going to walk us through this whole process of latitude-dependent gravitational fluctuations. And after that, next week, Vanby will be following up with a presentation on refraction. So some Globe lads had some, quote unquote, refutations to his what he was putting forward with the boundary layers of creating a plane for the image to be projected on, etc. So he's going to be going over that. And then the week after that, on the 18th, I will be closing us out for the season. We'll be taking a couple months off, and then we will return in the early spring. All right. Let's
Nice.
whenever you're ready, Shane G.
Nice. All right. So I don't think I have any videos. We don't need any sound. We don't need any echoing. So we're going to go into contextual gravimetry, as we put here, the measurement of gravity or Earth's gravitational field. Now on the cover here, very indicative of what we're going to be talking about are the two models that are put together to create what we know as the Earth. Right, so these ellipsoid model and the geoid model are going to be put together to form the datum, which we're going to use to reference the Earth. And so essentially, we're going to create an abstract spherical coordinate system out of these two already abstract spherical coordinate systems, and we're going to call that the Earth. So starting at the beginning, of course, gravimetry, as it's called, is a subset of geodesy and used to measure the acceleration down. Now they call it due to gravity, so the denotation is usually little g, but we're going to use little a because it's just going to be called the acceleration downward, or as we're going to see, local acceleration. To measure this, they have tools called gravimeters, right? A tool that measures gravity, or a meter that measures gravity, you think about it. So a gravimeter. They only measure the local downward acceleration of 9.8 meters per second squared, however. Usually they do so with spring balances that measure differences in gravitational acceleration by weighing a suspended mass at different locations. Some of them use interferometry, optical interferometry, which will bounce literal laser beams off of atoms of minute matter, which then tracks with extreme precision the rate and the change of the rate at which things fall. Now, speaking of latitude dependency, there is, of course, supposed to be a variation in the strength of the gravity field as Earth spins and produces centrifugal force. And also, as the latitude dependency would suggest, it's supposed to be different at the poles than it is at the equator. Now, typically, what it would look like, and what they say it looks like, is something like this. Right, where if you had a 9.8 meters per second graph. Now, then important to note, this isn't actual data as far as I can tell. I cannot find actual data that shows this. They say that all data ignores this. So this is the presupposed model of what they're, quote, ignoring. And this is the widest fluctuation in the measurement using gravimetry of, roughly 9.83 to 9.77, depending on where you are. So slowest at the equator, fastest at the poles. Or strongest at the poles, you could say. So that's what they ignore when they do any sort of gravimetry, strangely enough. So they say that this is ignored. This is latitude dependency is actually introduced afterwards based on the corrections interposed because of the model, because they assume an ellipsoid model that has that latitude dependent corrections. They incorporate that into measurements that they make. We're going to watch a video at the end that goes over what they think causes this and how actually they think maybe it doesn't cause that at all due to a massive scientific coincidence. So they say that the raw gravimeter readings do contain this latitude dependent effect, but the correction that they make is based on the assumed reference ellipsoid and rotation, not something extracted or be able to be visible in the data set. So that's strange. That's strange. The first, of course, gravimeters were just vertical accelerometers, and of course, dropping a test weight and then measuring the difference at which it drops. Quickly, we'll go through some of the scientific references here that they go through, because they talk about absolute gravimeters, relative gravimeters, what each one measures. So this is an excerpt from the ECGS, which is just the European Center for Geodynamics and Seismology. And they say that gravimeters are the instruments used to measure Earth's gravity field, which again, they denote G, which is a function of the geographic position of the observation sun and a function of time as well. So that is very important. As we're going to see, tiny variations in the downward acceleration can be measured, but as well as being a function of distance and geography and placement, it is also a function of time. As we'll see at the end, this supposed anomaly field changes over time. So if it's based on relative density, then the supposition would be the relative density of the Earth is changing and undergoing waves over time, which would be quite a thing to claim. Now, when they ask them what they're measuring this difference in G again for, and again, they're ignoring the biggest change between 9.873 or whatever, and between 9.7, they're ignoring that, and they're saying the tiny variations from the ellipsoidal normal is what they're actually measuring. And they say they need that level of precision for determination of the geoid, meaning the number one cause, the reason why they do this is to create the geoid model. That's interesting. And all the secondary causes are for tectonics and post-glacial rebound. So that's like PNS waves and climate change stuff, which they can, suppose some more in there. Atmosphere, cryosphere, and hydrosphere, the structure of Earth's interior, where they're guessing at density layers. And then geology and mining, which has to do with guessing at density layers. So they're saying that the main purpose for why we need all this and why we do this is the determination of the geoid. That's very honest. I find the rest of this secondary, really, and that the main reason for any of this is the determination of the geoid model. So an absolute gravimeter, let's see, was again using a test mass that's allowed to freely fall inside a vacuum. And then this one would use an interferometer, time within atomic clock, to then measure the wavelength to get the actual variation in the rate at which it drops. Super precise way to measure what we agree on is the average speed at which things fall to the ground locally. Again, we haven't discussed the reason why things are falling or just measured the reason. We're only measuring the fact that they fall, and we're making a kinematic measurement of the rate at which they fall. We're not doing anything to do with the reason that they fall or the cause of the reason for the force, or that would be gravity. We're not doing any of that. We're just measuring the rate at which things fall. So again, back to our friends at the ECGS, the European Center for Geodynamics and Seismology. We're going to look at what an absolute gravimeter looks like. This bad boy is called the FG5, and it's installed in the Wolferdane underground laboratory, which looks a lot like a lab school basement. But here's what it looks like in all its scientific rigor in the field and in practice. Super precise, highly scientific instrument for sure. I don't think anyone's denying that. It's definitely measuring the rate at which things fall. And we all know that things do fall. We all agree that things fall. We only disagree why things fall, or the reason that things fall. And you can tell by the relative blue light how scientific this procedure is for sure. Going a little bit further, they have a superconducting gravimeter, which they call the GWR, also in the same Wolferdane underground laboratory over at the ECGS. Here's what that bad boy looks like with its own hard drive running off of the side. But you don't need to get that complicated to use a gravimeter, as our boy Ken on Twitter pointed out with some of his recent posts exploring how gravimeters actually work, where they're just measuring local G, or in this case, field acceleration, local A, by usually measuring the rate at which things fall, and then the delta change, so delta G or delta A. Field acceleration is what they're showing. And again, it's differentiating that this has nothing to do with mass attracting mass. This is just measuring the rate at which things fall. This whole mass attracting mass supposition is forced into the model later, for sure, via the geoid model and its modeling, but not in the actual measurement or obtaining of the data. Again, his key takeaway here was a gravimeter gives a reading even if no massive object is close by. That's because it's just measuring the rate at which things fall, not anything to do with mass attracting mass. Interestingly, if you wanted to speculate about the cause for the dynamic reason for why things fall, and if we were to interject, say, an electrostatic cause, then something called the dielectric explanation would make more sense. because this is something that they specifically have to account for in the taking of measurements using gravimeters. So when they don't have to account for much, but the dielectric conditions, they absolutely do. Denser and more conductive materials obviously would locally distort the field, and you get sort of a similar variation based on density for an electrostatic cause versus Newtonian. But we're not going to really mess with any of that. We're not going to disagree with it. We're just going to deal with the local A and the measurement of the local A and how it changes. And again, as we said with our latitude dependency, it does change, but this is not the change we're going to be focusing on. This is not the change the world geoid model is built on. This is not the change of the models that they publish. The published models and data and sets all deal with deviation from ellipsoidal normal, which is, the assumed perfect gravitational and centrifugal force and latitude dependency that we talked about. So it does fluctuate, but by a tiny amount, right? By about 0.4%, or from 9.78 to 9.83. As we said earlier, that looks like this, 9.78 to about 9.83. And this is, again, what gets ignored when we start using models for the geoid and we start taking measurements. Now, we can go into real quick why 9.78, like why do we get 9.8 meters per second squared? And we can just take it on its face that it has nothing to do with the big G or the cause of gravity. We're just going to measure using this kinematic equation here, where the height is 1/2 the acceleration times the time squared plus dt. So we're going to remove this term over here. We're going to simplify it and say the velocity is 0. So we're just going to do the rate at which things fall downward. So we're going to be dealing with the height and the time. So then we simplify it, algebraically shuffle it around, solve for A. We end up with A equals 2 times the height over the time it takes to fall squared. And that is all we're measuring with our gravimeters. This is all what gravimetry is based on, is the deviation in this tiny measurement. A equals 2 times the height over the time it takes to fall squared. So again, here's this, why it doesn't appear. There's no big G in here because this is just kinematics. This is just motion. This is just an observation of the rate at which things fall. We're doing nothing for the cause for why things fall, just observing and measuring and calculating the rate. Now, I think globe proponents on Twitter and people who probably don't know the inner details of this would argue that you can't have this without this. However, there's actually no link between this and this, as we're showing. The logical link comes afterwards when you physically solve for this, then you insert it into this to make this equation work. And this is built on this already equaling 9.8, right? So this is the only one where you can solve for locally and will give you the correct answer every time, assuming your variables are correct, right? So this is what they're saying causes it, but this is independent of this. So this shouldn't be independent if this is the cause. That's the argument. And to break it down a little bit further, our little a is just, again, 2 times the height over t squared and does not directly depend on any gravitational constant, but gives you a neat way to calculate the acceleration downward from the distance h as an object has fallen and the time it took to fall. So that's all this is. That's all this is showing. So it's saying that if you drop an object from rest and measure the time it takes to hit the ground, you can calculate the acceleration using this basic formula. Put it in a real world example. I'd like to use this example over here. And the only 2 parameters you need are here. The height it's dropped from, this is our h, and the time it takes to fall is going to be our t squared in the equation. Right. So if a thing, you drop something from 10 meters and it takes 1.43 seconds to fall, you can quickly solve, plug that in. 2 times 10 over 1.43 squared equals 20 over 2.0449, which when factored out, of course, 9.78 meters per second. There's a couple other examples you can work through, but the result's always the same. No big G, no cause for the downward acceleration ever inserted here. Take a quick look at chat. How we doing with chat? Everyone's chilling.
Are you sure there's not any gravitational potentials and masses involved in that? It's not hiding in there somewhere?
You can always insert it afterwards, as we do over here. But yeah, in the actual calculation, no, completely gone. Like, you don't need it at all.
Nice. Yeah, chat's looking pretty good. They're breaking down the numerology of Big G as well. So we're taking it on all fronts, dude.
Nice. Yeah, so the way it would work is they have this formula, and then you rearrange it, and then you solve for this separately, and you plug it in. It's a plug and play, right? So the relationship here is not dependent on this causing this. Its relationship on this having a value, which is presupposed into this constant, etc. So that's where that comes in. That's how that works. So the argument would be that the dynamic cause is then supplemented by other knowns, and they invoke other suppositions like tied in celestial mechanics. So it would go something like, mass attracting mass is valid because we know that we use Newton's gravitational law for celestial mechanics, satellites, etc. Now that's also fallacious. We know that they don't actually do that. That's not how that works. They use an ECEF and an ECEI, so a coordinate system transform between Earth-centered inertial and Earth-centered Earth fixed, so that they can hide the C plus V value, which is independently dependent on the velocity of the ether, which they then sync to sidereal time to remove that relationship so that they can do all the calculations within ECI. So that's certainly not something that relies on the dynamic cause of mass attracting mass for any sort of predictions. They say tides. That's also not right because we know that goes through Newton's gravitation. They use lunar tidal acceleration to calculate with a constructive gravitational wave interference when the moon is at new moon. So it's the neap tide, which is the highest tide, is when the moon and the sun are in close proximity. And they say that the math then produces constructive gravitational interference to get the tidal and lunar accelerations in line so that the sun can exert a gravitational force higher than the moon. That's also not how that works at all. So we can disprove that as well. So really, the other evidence for this being mass attracting mass is not evidence at all. So we're still, at its heart, dealing with little a. Little a is just the kinematic rate at which you observe things to fall. So can you substitute little a for g? Of course, all over, everywhere. Everywhere you see little g, in most formulas, you can just put little a. Just to run through them real quick, because the Glober lads will point this out. You can't have buoyancy without gravity. You can't have mass without gravity, etc. Well, not really, right? You just swap out your little g over here and the buoyancy formula for little a, in which, again, you can solve for little a on the fly. Little a becomes 2h over t squared. So then this could easily be b times 2h over t squared times v, and this will all work the same way. No dynamic force of gravity required.
Are you stealing gravity from them, Shane? Are you thefting it
And
right now?
buoyancy.
Right.
This is the theft of buoyancy we're watching.
Yeah, I think he's just stealing the variable, and yes, the presumptive cause for the variable. I don't think he's stealing anything. He's just doing a quick old swap there for what really matters and leaving that in the equation.
I don't know. There's rumors that he's stealing gravity, Stone. He's stealing it by showing this kinematic equivalence here.
Yep. So again, this is why we're talking about little g, because this is what gravimeters are purporting to measure the variance in, and we're putting forth why a variance in the rate at which things fall locally doesn't really matter to us. We would observe it and expect it, and we can use all the same formulas. So again, they have mass defined as needing little g. Nope, swapping out little a. You can just have it the same thing, swap out little a for 2h over t squared, and you get the same description of mass without having to invoke gravity or as a dynamic cause of anything. Same thing with weight, swapping out little g for a, and density isn't really affected, but you can do the same thing. And that's sort of how you would interpret why you don't need gravity for local acceleration and any of the formulas that rely on local acceleration, like buoyancy, mass, weight, etc. Now, in the field, when we go into how they're going to measure it and what they use and what they're dealing with, again, while they know that it varies, they apply corrections that are supposedly accounting for instrument drift, earth tides, latitude dependency, the free air corrections for the anomalies. All of that goes into their model. That's built into this model, which then yields this, which is the deviation from this. This isn't showing the latitude dependency of the actual variance in little g as measured all over the Earth. This is showing the deviance from their presupposed centrifugal perfect latitude dependent model. I know that's a lot. You would think that this would just look like the gravitational field, but no, this is the gravitational anomaly, and they rate anomaly by the deviation from this. So in that way, they're removing this entirely from this, and what they're left with are these tiny, minute, barely noticeable fluctuations in G that far underseed what we're looking at in this mighty fluctuation between 9.8 and 9.77. So, again, all the maps, all the models, everything that we look at discounts that giant stripes of latitude dependency to get there stabilized, which is again showing as the deviation from the reference ellipsoid only. Crazy. And I do claim that when you take raw gravimeters measurements, you'll see that the latitude dependency is baked into the measurements, not the corrections. They say that, but the model again instills the corrections back into it. So even if they weren't there, if you put them into the model, they would definitely be there anyway. And what we look at in majority are the gravity anomalies, where it's, again, deviating from normal, and normal would be from the ellipsoidal normal. And it's such a tiny, tiny percentage that we're going to go into that it's very funny. And again, because so the claim here is that the geophysicists care only about the anomalies, which is department from the reference ellipsoid or the reference Earth, and that the standard practice is to subtract the reference ellipsoid gravity, WGS84 or the GRS80, which is the gravitational model, and then publish the actual anomaly maps, which is what we see all the way over here. And that's what we see commonly under the field of geodesy with geoids, right? This is a warped out geoid model. This is what you would look at with the geoid model. And just so we're clear, the actual model here, the variation that this is showing is in mellagals, which is this over here, and it's in a tiny, tiny amount, and it only varies 50 milligals either way. So you can see it go from positive to minus 50. That means that the giant fluctuation between this super high peak and this super low valley is no less than 100 milligals, and that's absolutely tiny. And it's not even within the 0.4% that we were talking about for latitude dependency variation. We're talking 0.005%, or in practical terms, plus or minus 0.0005 meters per second squared. That's what this whole model is showing you. A tiny, tiny, tiny variation, which apparently is super important to somebody.
Just to quantify the roundness of that, we're already dealing with 9.8 meters per second. And this is, instead of 9.8 meters, 980 centimeters, this is 1/2 of 1 millimeter. Right.
Yeah. I was down with tracking the latitude dependency and trying to prove the model, but then to find out that they remove and discount all of that immediately, only to focus on the deviation from their presupposed ellipsoidal perfect. They assume their reference model at 0, and then any deviation from that they mark. And then you're left with this, and you go, ooh, look at the shape of the Earth without oceans.
That looks so intimidating and so gravitational. Like we got a red section that's obviously where it's the strongest, blue where it's the lightest. I mean, but then when you look at the numbers,
like they've already removed all the deviation that would matter, and they're focusing on these tiny variations from their superimposed ellipsoidal normal. Crazy. So we know that the models are super important. We know that they have an ellipsoid and a geoid. We know from other presentations, the 2-sphere model, that there's a terrestrial and celestial sphere, and that we know the terrestrial sphere is mostly made up of this ellipsoidal model and long lat. So adding to that is that we have a geoid model, and the geoid is derived from the ellipsoid, not the other way around. The geoid is not independent of the ellipsoid. You cannot have a geoid model absent an ellipsoid. They are not they're interdependent and interrelated. And this one can exist without this one. This one cannot exist without this one. I hope we're getting that clear. So a reference ellipsoid like the WGS84 is always needed to be defined first, because the geoid model is then built on top of and within your chosen reference ellipsoid. So it's then often computed as the difference.
Did they actually write it like that in the previous slide from a manual, where it's like section 2.5, the geoid is derived from the ellipsoid, comma, not the other way around? Like,
yep.
It's
just a computational reference.
Like, don't get this confused, guys. That's hilarious. Just as plain as you could make it, right?
Yep, because some people claim the opposite. It's usually the people who are in the field who only deal with the geoid model. And like I keep saying from the Truman Show reference, right? We accept the coordinate system with which we're presented. If everything you're given is tied to WGS84, your output is WGS84, you're doing translations within WGS84, then yeah, you could be forgiven for thinking the world is actually WGS84. But if given another model, then you would say, hey, this model actually can exist absent this model. which is interesting. So again, they explicitly reference their specific ellipsoid, and any change in the ellipsoid will change all the geoid heights. So the reason that this is specifically referenced is through the metric of heights, which we'll go into a little bit specifics later. But essentially, there's a height. Geoid height is n in the equation, and the geoid height n is based on the ellipsoidal height underneath. So if you have a situation where the ellipsoidal height changes, then your subsequent additive geoid height also changes. So literally, changing the ellipsoid would change all of the heights of the geoid, and that's why they're inextricably linked. So if you Google, say, gravimetry, gravimeters, GNS, and how it's all interrelated, you'll get a nice Google graphic that's super impressive that looks like this. Then it's like land, sea, air, satellites. Wherever you are on the Earth, you're measuring gravity, right? Gravity's everywhere. It's unavoidable. We know it's super real. And again, can't stress this enough. What we're measuring is the rate at which things fall down locally. And we all know the rate at which things fall locally. And this is trying to measure the changes by ignoring all of the latitude-dependent variation. So this is heavily focused on the geoid model and their model over here, which is GRS 80, and trying to get and how they pin this down and measure it, and all the interrelationships between all of these tools and levels to get that they're inner mass anomaly. And what they're claiming to measure here, of course, is the specific force acting on this plane as it goes this way, and they're kind of measuring out through vector addition what it would be as their local downward acceleration only. So they get these functions of forward acceleration, and they're simplifying to get the change in just local g. A little bit more complicated is this over here, and this is how they get you with, this is how we're measuring Earth's gravity field with our GNSS satellites and our relay stations, measuring our trajectory over the ellipsoid by perpendicularly subtracting our vector addition or our vector added 10 meters per second squared downward, coinciding with our GNSS ground stations and pinging our satellites up above, all of course, running on WGS84.
Oh, wait, though. That's not 10 meters per second. That's 10 micrometers per second.
Dude.
Off by a million, 6 decimal points, which is why you see what's in the yellow box at 10 to the negative 6. Yep. Yikes. Yeah.
This whole map is actually in terms of 10 to the negative 6. Like, that's what they're looking at for sure. And that's what they're saying is happening here. So again, they're measuring the specific force at the instrument. They're using all of those fancy tools and references to create the anomaly model, which is, based on their spherical assumptions and the ellipsoidal model in the first place, which then produces their 3D gravity geoid model. So when you take all that data from this and you say, look, it produces this because Earth's a sphere. Well, the processing that you're using to relay and interpret and gauge and ascend and model and add all the data actually already explicitly models the gravity field as the near oblate spheroid. So meaning you're already using geodetic coordinates, ellipsoidal heights, spherical ellipsoid harmonics, data interpolation based on, averages, mean processing. Everything that you're doing is assuming this model. And some of the processes wouldn't function unless you had previous knowns of your curve fit, which is why you need the spherical model in the first place. So again, the figure itself is not showing, it's very, very small gravity variations, 10 to the negative 6 or whatever. And that they're trying to measure against geodetic reference frames. Now, if we can go into the importance of the heights real quick, when you're having a height, when you're trying to measure heights above an ellipsoid and the surface of the actual Earth and the geoid, this is how they confuse everyone. This is also how they wrap level and horizontal sea level, or flat sea level, around an ellipsoid model so that you can define level as curved. When they say level actually equals, means curve now, which is level above a curved surface, is because they took level sea level measurements and wrapped them around this reference ellipsoid through this exact method, using orthometric heights, ellipsoidal heights, and geoid heights. So you have n, little h, and big H. Now in this diagram, the only thing that's real is this line up here. This is the surface of the Earth on a hill. Here's the surface of the Earth as it goes over here. There's a tree on a lower part of the hill. There's a house on the top of the hill. And this is the only actual height. So they call this the orthometric, the surface height. Below that somewhere is an undulating geoid, which is roughly spherical from this gravitational measurement deviation from the ellipsoidal normal. And underneath that is your reference ellipsoidal normal from which heights are determined in your geoid. So all of this is to describe a house on a hill with a tree. They need all of these heights. No, you only need all these heights when you're wrapping them around a model, and only then can you get actual level heights wrapped around your final 3D modeling height through ellipsoidal heights, geoid heights, and orthometric heights. And again, ellipsoid height defined over here is the difference between the ellipsoid and a point on Earth's surface. So it starts off with a comparison. That's also called the geodetic height. Different from that is the geoid height, which in the equation was big N, which is the offset of that value between the reference geoid and the actual ellipsoid models. And then finally, big H, the only one that's real, the distance between a point on Earth's surface and the geoid. So that's not even really real. This is the orthometric height, takes what would have been a real height and subtends it with a geoid. So they have to use geoid as starting reference normal or 0. So that's crazy. That's how you wrap flat mean sea level references around an oblate or ellipsoid spheroid. And by you say you're accounting for gravitational irregularity. So that's the importance of some of the models that they're using to, quote, measure gravitational variations and anomalies based on their presupposed ellipsoidal normal. So again, the geoid acts as a gravity equilibrated zero surface that deviates from the ellipsoid, allowing the subtraction of the n from the GPS-derived h to yield big H, which does drape a conceptually flat equipotential sea level over the sphere-like model of Earth. Without this, ellipsoid heights would misrepresent true elevations relative to the global mean sea level by ignoring, quote, global local gravity anomaly. So without this, it wouldn't work. And through this, you get what's called negative heights. And through negative heights, you can manually force level measurements to curve downward perpetually. That's how they do that. And this is all definitely related to the geoid because they use this model within the ellipsoid to reference all three together. And again, this is one of the the models that we're correcting. This is the geoid model, the height of the geoid, which is the geoid 18. Electromagnetic model is the EGM 2008, and a WGS84 is our terrestrial sphere model. So all of these are related to each other. So again, if you're using a geoid within your ellipsoid, just think about how your semi-major axis or flattening factor, which is particular to your ellipsoid model, it's the only differentiating factor between them, how changing that would affect all the subsequent and relative geoid heights within your model. So you'd have a different geoid height, which then meets a different geoid model. Now, in our previous presentation, we were putting the celestial and terrestrial sphere models together, and that was the argument to create the globe Earth, which was the combination of two abstract coordinate systems. And using the celestial and terrestrial sphere combination, you get an introduction of an astrogeodetic deflection, also known as deflection of the vertical, meaning when you're taking a point on either of these grids and you're forcing these grids together, so you overlay one over the other, any deviation from that point within these grids, it gets qualified as the deflection of the vertical, and they say that it's a mean difference between the astronomic latitude and the geodetic latitude, and that they take these measurements and put them into books, and that's how the deflection of the vertical gets born. It's essentially a subset of astrogeodesy, which is itself it's a subset of geodesy, just like gravimetry, and that what they're doing is transforming astronomical coordinates into geodetic coordinates. So that's what we were comfortable with before, but now we're going to add a whole new metric, and we're going to complicate it a little bit. This is the model that you'd see on the internet for our ellipsoids. Hey, our wonderfully complex spherical Earth that's totally real. Because of this, because of how real it is, we have to create two separate spherical ellipsoid models to model the realness of our real model over here. So this is what you'd see on the internet, is that independent. We create these two models because our Earth's a sphere. And what I'm going to argue is that it goes the other way, is that actually you need these two together, and these are two separate abstract spherical coordinate systems, and this one again heavily based on and related to this one, and this one itself an abstract spherical assumption to begin with. Those two together, the geoid plus the ellipsoid, gives you the datum, which is what we were using for our terrestrial sphere model. So again, geoid, ellipsoid gives you the datum, meaning that they would actually look like this. You can't have this without your geoid and ellipsoid models being shoved into them. Now, we were going to touch on the cause just a little bit because, again, their claim with the gravity density maps and variations and anomalies is that they're measuring a variation in mass attracting mass, but they're not. They're only measuring and recording deviations in the local acceleration. So the rate at which things appear to fall locally, that's what they're measuring. It's only through this interpretive framework that they then pull through of Newtonian / relativistic gravity that they impose on those readings, which is then imposed via the modeling that we started with, which is then bringing up our supposition of negated and ignored latitude dependency for such measurements, which gets ignored within the model. So again, back to our kinematic equation, it's separate from asking why. We just describing how it moves, which is right kinematics, which is little g, or as we were calling it, little a, which is our average of 9.8 meters per second. Dynamics would be why g exists. And again, when we use the formula, they just plugged in what you measured as little g into your big G, and they said, behold, big G causes little g. Not actually proven in any of the math. The logical chain that they sort of suppose is, since mass attracting mass is a force, they define it with gravitational potential. They compare that and they say, look, because we know it's a force, we know that little g's difference is because of this force. Crazy circular. Nothing is ever proven. This is never used in actual conjunction with any sort of constant or the big G itself. Not to mention that they shouldn't be arguing that they're measuring mass attracting mass. They should be arguing the newly enhanced interpretation of the cause of gravity, which is the curvature, bending, and warping of space-time, which this is enforced via linear geodesics, which then induces the bending of mass, which then forces masses together, which is what causes mass attracting mass, as our new boy Einstein would say, as he improved upon the Newtonian dynamic cause of gravity. So when they say it's not mass attracting mass, well, it's just the bending and warping of space-time, which is all super related and very cool. Anything to say about that, Alan?
Yeah, it checks out.
Okay.
It's just like the big feature there he did there with general relativity with the geodesics and whatnot is that when you're in areas of like low gravitational potential and mass and stuff, that there's not going to be any bending of space time, and it's just going to fall back to Newtonian dynamics. So they get to have it both ways in that regard. They can just be like, well, you wouldn't expect it because there's not enough mass, and then when you do, they're like, well, it will. And then when it doesn't work, they're like, well, it doesn't work because of general relativity, because it's actually bending and warping. There's just a little bit, just not a lot. So
Yep. Expertly put. Absolutely. Says it replaces the idea of a gravitational force with curved space-time because of mass energy equivalence, etc. Everything is thus free falling around simple geodesics, and that's curved geometry, which of course you can't measure with interferometry as a separate aside. And then that is the local gravity field, which is the manifestation of space-time curvature in a coordinate system.
Do you know how much money you would make selling, like at Home Depot or somewhere, a curvilinear tape measure? That would just be awesome, wouldn't it?
Curvilinear, yeah.
I'd like to own one of those. I need one. Give me one for Christmas.
Man, so again, all that to say is that none of this is dependent on Big G. None of what we've done, shown, measured, none of what the modeling entails, none of what the measurements show, none of what gravimeters actually record have anything to do with Big G, mass attracting mass, or the dynamic cause of anything. It's only ever been about this local acceleration or the change and the rate at which things fall locally. Now, and like I said before, all of the mass attracting mass or gravity in space-time is all introduced via a interpretive framework after the fact, and a way that they interpret the measurements is through that interpretive framework. So some people have, I think, argued to some of the lads that, they use a gravimeter to show that the surface of Earth is curving. Well, no, local gravimeter measurements cannot and do not ever show curvature. An absolute gravimeter would measure the local acceleration at a specific point, but anything you're talking about as curvature is only introduced ever through the model and its alignment to spherical models like latitude and longitude, not direct curvature measurement. All of the measurements that you take and record based on geographic latitude and longitude, introduce the certain shape, which is, of course, an ellipsoid or a sphere to fit your geoid data. As we said before, can't have a geoid absent your ellipsoid. The geoid exists within the ellipsoid. All of the heights are interrelated. If you change your ellipsoid height, the geoid height, of course, changes all over the place. Now we're going to get into some of the maps that we're looking at. This is the supposed proofs of Earth's sphericity. Here's one of our models. This is, of course, the orthographic globe projection. And here's our wonderful gravitational anomaly map of Earth's gravity field. Again, can't stress this enough. Ignoring all of actual Earth's gravity field with its latitude dependency and its band at the equator and its latitude bands. And we're focusing on tiny milligauss worth of variations from our assumed ellipsoidal normal as 0. Can't say that enough. And as we hinted at the beginning, not only does it deviate, it deviates with time. This is by month. This is 2008, and this is the month. So that as the month calculates on, we can see that the variations in Earth's gravity field, and again, this is the anomaly field, so it's the deviations from the reference ellipsoidal normal only, and even that changes wildly in their term, and this is only 20 to 20, not 50 to 50 milligauss, but here it is changing wildly over time.
Yet in other parts, like Northern Africa, it doesn't change at all. There are plenty of those zones that are just yellow the whole time.
Yep.
Just sitting right in the middle. Yet these other places up and down, up and down, up and down. Yeah, I'd like to see an explanation for that too. That'd be fabulous.
Just got to get out my gravimeter and we'll take some comparative measurements. We'll eliminate all the actual variance and we'll see what we see when we assume a perfect sphere. So as we covered, I think, ad nauseum, there is a variation supposedly, and why they say it measured with latitude. Now, this is what the model claims. We're going to watch a video of Neil deGrasse Tyson, I think, saying maybe that isn't the case, but this is what the model claims. And again, when all measurements come in, they ignore this to focus specifically on these tiny anomalies within the variation. So again, this is the most recently published Earth's gravity anomaly map. And we can see the tiny this one goes to negative 60 milligauss and positive 60. So again, that means that the difference between the highest high over here, or the lowest low, and the highest high over here is only 120 milligauss. Crazy. If we were to take this known projection and put it to another favorite projection, say our orthographic globe for the globe lads, here's what it would look like at this point in time, we have to say, because we know it changes. Or we can show it to our azimuthal equidistant lads, if you prefer the AE projection, or as this is becoming more important, the azimuthal equal area. People like to show it that way. This is your chosen interpretive model for Earth. Or, of course, we have the dual pole lads, if this is your chosen interpretive model of the graticule for Earth. And then this is how you would look at the gravitational anomaly variation of 120 milligauss. This one's a little bit better, a little bit unclear. You have this anomaly going from blue, which is way over here, 180. This is the lowest, all the way to the highest, which is just 80, which is the red over here. Wrapped around your Earth, your orthographic globe would look like this. Wrapped around your azimuthal equidistant would look like this with your little anomaly over here. Again, equal area. Dual pole lads. This is what the anomaly map would look like to the dual pole lads sitting over here. This is what they call the air gravity anomaly. So it's from a different comparative geoid height higher than everything else. And they get the anomaly comparative that way. And we see our scale on the right here again between 80 and negative 80 milligauss. And again, through our various projections, through our, again, this is the EGM 2008, and this is through orthographic globe. This is through azimuthal equidistant, your AE lads, if you will. Your dual pole lads centered at Africa with 0 longitude, et cetera, et cetera. All this is to show is that this isn't, model dependent. This isn't big G proof of anything. This is just variation in little g when you compare little g to a perfect ellipsoidal model. That's all this is. I would think that the actual model itself with the latitude dependencies would be more beneficial for anyone using it for anything, but apparently all of the field of geodesy disagrees, and then everyone focuses on these tiny anomalies only. And again, this is our breakdown of little a, independent of big G, and the rate at which things fall, independent of the dynamics of where big G comes from, and mass attracting mass, Newtonian dynamics, etc., just to wrap it up. And again, in modern geodesy, the geoid model is defined relative to a reference ellipsoid, and it cannot ever be independent of it. If that is the only thing we're stressing today, that's what we should take home. Once defined in terms of the ellipsoid, it has no model exclusive proof, certainly isn't proving curvature or the shape of the Earth in either way. It's an internally self-referentially consistent model called WGS84, also known as the reference ellipsoid or your terrestrial sphere. And again, on the internet, you will see that the model dependency with arrows is said to go this way. And because we have this Earth, we can make these models. And I think I've shown, and I'm going to argue that no, it goes this way. Because we create these models, people confuse these for an actual spherical Earth. The question we would have to ask is, if these are just abstract spherical coordinate systems put together to make the Earth, then can you differentiate your abstract spherical coordinate system, ellipsoid and datum, from the physical Earth? And if you can't, then you probably have a problem. And again, this was the old model putting together the terrestrial and celestial spheres to make the globe Earth. And I think now the updated model should be, we take our geoid and we take our ellipsoid, we frame this one within the other. From that, we add our celestials, we get our astronomic geodetic attitude, deflection of the vertical, which then creates our terrestrial sphere, which when put all together finally gives us our globe Earth model. There we go. That's all I got on gravimetry and the local acceleration.
Fantastic breakdown.
Neat trick, bro.
Right? It got us again, dude.
A series of interlaid conceptual models put together, told to us as reality.
That is what it is, dude. A series of overlaid conceptual spherical models. That's where we're at.
I saw them sneaking Cavendish in there, man. I had a good chuckle even from the second or third slide when they were referring to the vertical component of gravity. That always gets a laugh.
Yeah, they try to like contextually, tangentially insert it by not actually causing or claiming that it's the cause. They just are like to reference it together so that you associate them in your head. I think that's the plan because they know they can't prove it. So they're like, well, you know, everybody knows that that's what it is or whatever. Nice. So a short one today. That was pretty short. How are we doing for questions from our chat? Anyone got any questions?
Good on questions. Everyone absorbed all the information. They're all laughing at the small variations and the non-latitude dependent variations that would be much bigger, that they're, you know, much sought after.
Nice. We can wrap it up with our
yeah, we can close on Neil deGrasse Tyson's.
Yeah, tell him Owen wants his bike back still.
I think I do need sound for this one though, so we'll do stop sharing, reshare. Nope, that's camera. Share screen with sound. So which means if I do this, you guys can't talk, I think, because you'll be echoing. Unless it's not the same as Discord.
Send it. Get echoed.
You got it. All right.
As we've been taught to think of it from childhood.
Right. The
color-coded countries.
Yeah.
All right. I was talking with a geophysicist colleague, and he was referring to Earth's geode.
A geode.
Geode.
Do you think he was talking to PhD Tony?
I just want to say, he's saying geode. That's not right. Geoid is a geode is a rock and a crystal is something else. You might be
precisely.
Looked at it. Okay, all right.
And I said, oh, tell me more. So they care about the geode because they want to know what defines sea level for the oceans.
Makes sense.
Okay. So what is the geode? The geode is the shape that the ocean takes in response to not only the gravity of the Earth,
okay,
but the rotation of the Earth.
Interesting.
So if Earth were just a perfectly smooth sphere with water on it, the water would be bulgy around the equator and it'd be thinnest near the poles.
Right.
That's outer surface is the geode.
Okay.
That's surface.
That's surface.
Now, Earth bulges. We are about 5 miles wider across the equator than we are pole to pole.
Okay.
Not only that, a slight detail, we are wider just below the equator than at the equator.
Something to be proud of, Earth.
So since we're squashed pole to pole, that makes us oblate.
Okay.
And we're not a perfect sphere. It's a spheroid. It's an oblate spheroid.
Okay.
Oblate
And we're
spheroid.
slightly wider below the equator, so we're a pear-shaped oblate spheroid.
Gotcha.
Okay?
All right.
Pear-shaped. But let's ignore the slightly below the equator part and just say, right on the equator, there's a centrifugal force that would make you lighter.
That makes sense,
than
yeah.
if you were on the poles. It's spinning.
Spinning.
Right? Your tendency to go in a straight line
Right.
will lift you off the Earth.
Right.
You can calculate. I calculated this.
Okay.
Okay? And you're a svelte 160 pounds.
That was the funniest thing.
All right. Plus or minus. Okay.
Plus, right.
So you can do it and you end up like 4 ounces less.
Oh, okay.
Modern scales that household scales don't even measure
Right.
that, bathroom scales.
Yeah, they wouldn't even tell you.
They wouldn't even tell you that. But we can measure it and we know. All right. So I
We know.
spent my whole life saying Santa on the North Pole would be the only person who would know his true weight.
Right.
Because on the equator, you're weighing less than your true weight.
Right.
True gravitational weight.
Okay.
There are two things messing with your weight at the equator. Because the Earth is bulged, you are farther away from the center of the Earth, and it's spinning. That's wrong.
Uh-oh.
Here's the deal.
Drum solo.
It turns out
5
everywhere
miles
on the
out of
disk,
30, 59.
you weigh exactly the same.
What?
If the Earth bulges from spinning, if you bulge at the equator, the poles come in a little
Come
bit.
down, right.
Okay? So now it sounds like I'm closer to the center of the Earth. I should weigh more. However, not the entire Earth is pulling on you. It turns out that while you are closer to the center of the Earth, there's less mass pulling on you. Only, you can do this, you can show this with calculus and Newton's laws of gravity, that if you are smaller from pole to pole, the only part of Earth attracting you is the sphere that is the cutaway between your feet and the center of the Earth. And that sphere does not include the bulging that comes outside of that sphere.
Okay.
Those factors combined exactly equal the factors that affect your weight here on the equator, because the entire mass of the Earth is pulling on you.
because you're at the center.
Okay, because you're at a
Widest
widest point.
Right.
Now, what is the sphere beneath your feet? It's got everything.
It's all of it.
All of it.
It's all of it. So these two things, these two, principles, if you want to call them, they cancel out.
Yes, they exactly cancel. The fact that you have the whole Earth pulling on you, yet we're spinning.
Right.
Okay. So you have all the mass of the Earth, but the spinning, so that makes you weigh more. But then you're spinning, that makes you weigh a little less. Plus, the Earth is a little wider, so that makes you weigh a little less. Okay. All of that.
You put it together.
It comes out in the wash compared to your weight on the pole.
Wow. So Santa's fat behind can walk down to the equator
And it'll weigh exactly the same.
exactly the same.
Exactly the same thing.
Wow. That's,
You need the rest of his. You can't just weigh his behind. You got to weigh the rest of him too.
I got to tell you, he's mostly behind.
So that's it. So actually, through a combination of galactic circumstances, there is no latitude dependency, and you'll weigh the same everywhere, according to Neil deGrasse.
He flipped his math. He says that you weigh less and you weigh even less. But the oblateness we're talking about here, remember, was 5 miles out of 3,959 miles. Like, consider that as a percentage. You know what I mean? Like, what is the difference you pretending to measure because of that influence?
0.000.
You got it. And it's divided over r squared, right? The change in r squared is just, it's so minute, it's not even worth talking about. Just amazing. And the whole geode thing was just entertaining as hell.
Yeah, like he's never looked it up once. No, he's never heard anyone say the terms once. He was handed a sheet and he reread first point blank what he thought it sounded like. That's my only explanation.
Oh, guys, he was talking to his geophysicist buddy the other day.
Who said it was all a geo?
Why would he lie, Shane?
Nice, yeah. So that whole latitude dependency we're talking about, it turns out that Neil deGrasse Tyson says it doesn't matter and that you don't measure it anyway. So maybe that's why all the models, instruments, and modeling ignores it completely. Who knows?
Well, thank God for the geode. You know what I'm saying?
Just to be clear, it is geoid. He is mispronouncing. He's using a different term. He's talking about rocks and crystals. Or like if you played Pokemon, geode was the rock, bro, right? It was a rock. That's all a geode is. It's a rock. He's very confused in his geoid modeling.
But still somehow miraculously correct. as is the case with science. Even when it's
But
incorrect,
apparently a
it's
bike
always
thief.
correct.
Yeah.
Well, regardless of the status of the bike. Yeah, what Karen just mentioned, there was a fella who said he was
Right.
measuring latitude dependency in Australia and then Antarctica where they, did the TFE. And so like that, what was measured then? Like Neil?
It must have been instrument error, and that it doesn't matter. So, what he was saying is actually your centrifugal force got canceled out by the gravitational variance, and that's why it measures exactly the same. So you're wrong.
And on that note, in pharmacology, they have really sensitive scales, down to like the milligrams of things, hundreds of milligrams or whatever. And those when a lab acquires scales from another lab, it comes with a maintenance log sheet, and you could see like when it was last calibrated and all that. My buddy's is in pharmacology, makes the medications and all that and stuff. And the lab that he works at just got some new scales, new to them rather than actually new. But anyway, it came with a nice log sheet. It's been all over the world, like 10 or 12 different locations, all different latties. It's never once been recalibrated for the weight. And they're dealing with things if like if the weight's off, for their medications and stuff, people will, get hurt. So there would have to be some sort of standardizing the weight differences per latitude in the medical field, especially in that regard where the literal weight of your medication dictates how effective it is and what it does. So the fact that they don't do anything like that to recalibrate it for their laddies and just kind of gives the game away, as Stone says.
So, like the fact that they know it's there, that they assume it's there, but that all their modeling, mapping, and engineering ignore and drops it completely from all existence was a marvel to me. I was like, oh, so that when you're building stuff relative to G, all you need is to the micro milligal variance on 0.0005 from ellipsoid normal. Huh? That's what affects it, not the 0.4 variance from pole to equator. Huh? That one doesn't matter for nobody, huh?
Nope.
Okay, you guys are the experts.
All right. Well, thank you for that awesome presentation. Stone, did you have any final thoughts to close out on that?
No, I'm good to go. I think we covered the bases on that condemnation for sure.
Awesome.
Nice.
All right. Well, we will go ahead and wrap up for the week. Join us on Monday for Celestial Theodolite update number 29. Tuesday, Ether Roundtable 112. We're going to be watching Bennett's interview that he did recently on the channel whose name escapes me at the moment. And then Friday, we'll be back for the Twitter community space. So check us out there. And then Sunday, we'll be back with Bambi to do a follow-up on the Globers demonstrations to try and explain how how an image gets produced in a homogeneous medium versus a completely separate medium to cause a sharp change for there to be a boundary layer, for there to be an image projected into that boundary layer. So we'll see what the Globe lads came up with next week, and then we'll be closing out on the 18th to go on break for a little bit. See you guys tomorrow and throughout the week.